So let me show you a couple of shortcuts here. All right, so for starters, we have this thing called string to int, right? That goes through and it finds the place and all this stuff and multiplies by 10 and all this crap. So what I'm going to do here is we're going to this is a multi-line comment. So when you start something with a slash asterisk and end it with an asterisk slash, that means all of this stuff is for human eyes only. It's not part of the program anymore. Okay? So all I'm going to do here is I'm going to return integer.parseInt of s. And the code's going to work identically otherwise. So this is a built-in method inside of Java called Parse Int that belongs to the integer class, and we'll talk more about why we called it this way at another point in time. But there exists a class in Java called integer that has in it a bunch of stuff that we can do related to integers. And one of those things is if you give me a string, I'll give you the integer version of that string. All right? So that would have made life a little bit easier in the homework assignment, but then you wouldn't have had the opportunity to write this guy. Right? I mean, how exciting was it to write that? It was fun, right? Like a lot of fun. Like you couldn't think of a better way to spend a Wednesday night. Huh? It is a brain exercise. How do you think that I keep my hair so... I don't know why it keeps growing back. It's just upsetting. I mean, I buzz it because I don't like the side part here, right? But that part keeps growing back. Why can't I just go bald? It'd be so much easier. Because I pretty much need to cut it again now. So I have sleep apnea, so I wear like one of those masks when I sleep. It like blows air into you. So when I wake up in the morning, like my hair's all like, you know, like folded funny from the mask I wear. I tried to wear my Superman cape the other day. It didn't help either. I do have a Superman cape too. Okay, so this makes sense. New way of squeezing a integer out of a string. Now, do understand though that this guy will have a, you know, he'll give you a runtime error if. So, for instance, if I say system.out.println integer.parseInt LOL or something like that, you know, it's going to scream at me. It's going to say, hey, I'm not sure what you're looking for here, but you are trying to turn the word LOL into a number. Okay, and it's going to give me an error. It's going to say, I don't know, parse int exception or something like that. Number format exception for string LOL. I don't know how to turn that into a number, okay? So you can get errors like that, but our code would have an error for that as well. Because we're not going to, actually, we would not get an error for that in our version of the code. We wouldn't get a correct answer, but because we use the index of, we get a whole bunch of negative ones because it didn't find an L or an O or an L inside of 0 through 9. So you'd be multiplying by negative ones, like placed by -1, and yeah, things would go south pretty quickly. Okay, so that's integer.parseInt. Now let me show you a couple of other tools that would have made, and we won't necessarily go back and rewrite stuff because it would make us change our logic a little bit, but I'll show you some other tools that would have made life a little bit easier for getting the individual tokens, the numbers and the operators out of our thing. So in order to show this, I first need to introduce arrays. I don't think we haven't looked at arrays yet, right? Okay. So let me introduce arrays here. Get our Keynote open. All right, but we have discussed arrays because if we remember, we were talking about the evolution of C and C++ and those guys, and so an array is a collection of like type values. All right. So for example, in Java, if we want to create a collection of integers, for example, I could say int array. That's the type. So open close square brackets is the array type. Maybe I call it AR and I say this is a new int array of size 10. Something like that. All right. And actually, just for a moment, let me make this size 4. So it'll be easier for me to draw. Okay. So I'm going to steal this this line right here. I'll create a new slide for a picture. We'll put that guy there. Oh, and by the way, just so I don't forget, I want you to save the date for something. February. Yeah. I want to say it's like April 8th. Oh, did Dr. Locklear already send it out?
Yes.
Okay, yep. So April 8th, it'll be here. I'll have more details as we start getting closer to that, but we're going to have a computer programming, I don't know, competition-y type thing here. It'll start in the morning. It's going to be like a 12-hour thing where we'll have groups of like 4 people, and each group will have kind of a stronger programmer and then a couple of weaker programmers, but we'll be doing something real with like mobile apps, like writing an iPhone app, writing an Android app. But we'll probably be using some third-party stuff connecting to databases. So I think it would be a really good experience for you, even if you end up deciding that, you know, programming isn't necessarily for me. Going through that experience and just, you know, being on one of the teams and being their weaker programmer, let's say, will expose you to kind of how software is put together, maybe more like in the real world, and you'll kind of get to see that system. And I think that will, at the very least, help educate you going into the IT side of things, so you kind of know how those things work. Because obviously in here you're getting, I mean, we're only kind of seeing more of a theoretical side of things. We're doing the applied, but you're not seeing it in like a real life application. When we get over to the next course, the 537 course, then we start doing it towards the end of this course, depending on how everybody is doing. But we sometimes introduce an Android application here at the end of this course. But definitely in the next course we do, effectively, it's an Android programming course, which picks up from topics where we stop in here. And I think those are all good skill sets to have. But I would strongly encourage you to save the date for that April 8th. It's a Saturday, and you know, come and join that thing. It doesn't cost you anything. You get free food. It's usually a good draw, right? Come to that thing, have fun. If you perceive that you are a terrible programmer, it doesn't matter. You know, we're going to have freshmen there who've never had a programming class. So it's all about just being exposed to that stuff, you know, and learning as much stuff as you can in a, you know, I guess kind of a fun atmosphere. So save the date for that.
The teams are put together on that day?
Huh?
The teams are put together.
Yeah, so I usually, well, I guess it's possible we might put them together ahead of that, but I'm usually the one who kind of puts together the teams, or at least kind of assigns like team captains. So, you know, I'll kind of say, if we have enough people for, say, 6 teams, I'll pick kind of our 6 strong programmers so that, you know, they can be mentors for the different teams. You know, then depending on, I guess a lot of times I'll lead a team, and a lot of times I'll put students where like English isn't their strong suit on that team. I'm used to dealing with that, where one of our sophomores might not swing so with that. So, but it is fun, and then I float around answering questions and that kind of stuff. But it's a good time, but you don't have to be stressed that you aren't any good. There will be people there that are better than you, anyways, and it helps them to teach you. So everybody benefits from the thing. So do save that date. I strongly encourage you to do it. I think it'll greatly benefit your knowledge, whether you can decide you're going to be a programmer in the future or not. I think it'll help a lot. Okay, so let's keep trucking here. Why do you want to capitalize everything? Okay, so if I define a new array, perhaps called AR, so this is a variable of type integer array, and he's going to be equal to a new integer array of size 4. Go ahead.
Can you just backtrack a little bit, explain a little bit when to use char?
When to use char in variables? Tell me more about that.
Char variable as opposed to, when we say all integers are characters, integers operators.
So maybe we say var types, and you want to do something like this. So if we had a slide, I think, last time that talked about the different sizes, right? Did we have this guy, byte, short, int, long, char, float, double, Boolean. We had something along these lines, right? Okay. So all of these guys are whole signed numbers. So whenever we want to do math stuff, okay, we're adding numbers, we're subtracting numbers, we're dividing stuff. We need to represent, negative 302. We need to represent, positive 128, things like that. We would use one of these guys. Realistically, we're almost always going to use int, and if that's not big enough, we'll use long. Okay, so this is when we need a variable for doing math stuff. So like today, we looked at our examples. We had a variable called firstNum that was a string, and then we converted that guy into a number and stored it inside of an integer called fn, right? So that fn, that first number, that was the integer version of that guy because we were going to do math with it. Now, a char type is a numeric type. You remember this guy's an unsigned whole integer. And this is related to the Unicode character set. So when we look at chars, if we look at the alphabet, for example, A, B, C, D, all those guys, they have a numeric value, which is what they map to on the Unicode character set. So for example, if I come out here and I'll just write some sample code in here. Let's say I do for char C is equal to A. C is less than or equal to Z. C++. And I do system.out.println. C. Let's do empty string concatenated with C, concatenated with a colon, concatenated with the integer version of C. This should show me the mapping. So it'll show me A and then what A's numeric value is. So let's just see this and I'll explain what's going on. So a lowercase a actually has the numeric integer value of 97. And that maps to A on the Unicode chart. Here's our Unicode. It's going to be a big enough picture. Not really. So Unicode has 65,536 unique characters. It's a superset of ASCII, which is 256 unique characters. So here's the letter A, and its numeric equivalent is number 97 on the Unicode list. So computers like numbers. That is, a char is represented as an unsigned whole integer. But when we use a char, so for instance, here in my code, if I just print out C, I mean, first of all, we can see that chars must be numeric types because I'm doing math with it right here. I'm saying C is equal to C plus 1. I started C off at the letter A. I said keep going as long as C is less than or equal to the letter Z. I mean, for loops are numeric things, right? We usually think about them as counting type things. So I'm saying go through all the letters between A and Z, and each time through, print out that letter. So there's all the letters in the alphabet. Now, the reason that works with math is because all the letters of the alphabet are right next to each other in the Unicode character set. So if I come in here and I said, don't treat that C as a char, instead treat it as an integer. That's what this says. This is called typecasting. So I'm putting parenthesis int parenthesis before that C. I'm saying, even though C is a char, convert him to an integer. And the thing is that he already is a numeric type. He just gets treated as a character type when we print it because it was flagged as a char. But I'm saying go ahead and take his mask off. Show me what's under the hood. All right, so this is going to show me the numeric version of the alphabet, how it maps, and you're going to see they're all in a row. 97, 98, 99, 100. So in the Unicode character set, all the chars for the alphabet are right next to each other. If you go to the uppercase alphabet, you'll see that they're different characters, but the same rules apply. Starts at 65, goes up to 90. Okay? So those guys are numeric types, but when we're using them in our software, we're often using them for their character equivalents, right? The fact that they're numeric types is more about how computers like to store things. That's the convenience of how they work under the hood. So your question is when would we use a char, right? Well, you'd use a char whenever you needed to store a character of some type. So this goes back to this idea of us saying the way we solve problems is memory, asking questions, and repetition. So when we're dealing with variables, we're talking about that memory side of things. So the idea would be if I need to store a number, if I want to remember the number 5, I might say int num is equal to 5. Now I've remembered that. If I want to store a character, maybe char question is equal to a question mark. Now I've stored a character. Okay. Now, practically speaking, something you might do is you might spin through every character in a string. So maybe we say string s is equal to hello. We say for int I is equal to I is less than s dot length I plus plus. And maybe each time through we want to go ahead and create a character named C, set it equal to s dot char at I, s.char@I returns for us the character that lives at position I in that string. I'm going to go ahead and store that in this variable called C. And now I can ask questions about that. So I've used this variable named C that is a special bucket that knows how to hold chars. Now the reality is that we just saw that C is actually something that knows how to hold numbers. But because he's labeled, we got a sticker on the side of it that says he's of type char. That says that Java, when we actually use those guys, will go ahead and do the lookup for us. So internally, it's going to store it as a number, but we don't have to know that. It doesn't bother us because at the end of the day, as long as we see it come out as a char, we're happy. So if I say system.out.println C right here, it's going to print out an H, then an E, then an L, then an L, then an O. We didn't have to know that the char type actually is a numeric type. I'm just telling you for personal knowledge and how things work under the hood, because computers store things numerically, which is actually going to be what your paper is about this next coming time as well. But because these things store things numerically, it makes sense for chars to internally represent themselves as numbers. But for us, all we care about is when we print it out here, that it comes out as a character. So there's my HELLO. Even though I can come in here and say, why don't you go ahead and show me the actual integers there? Don't do the conversion for me. And this will show me the Unicode values of those guys. Right, so the answer to your question is when you should use a char is it would be the same answer of when you should use any of the types. Use a char when you need to store a char. Use an int when you need to store an int. You can do math with chars. I can say something like this. I can say, I'm not saying it would be common, but I can say char C is equal to A. And then I can maybe do something along the lines of this. C plus 3. Doing math with it, this is going to add 3 to C. C start off as, whoa, missing semicolon there. That gives me a 100. Why is that? Well, it is, but C is a char type. So C is a char, but Java sees this plus sign there. And it says, oh, well, do you mean math or concatenation? Oh, this is not a string. This is not a string, so you must mean addition. Therefore, we'll go ahead and add these guys together and give you the result. Well, in order to add these, we're going to have to convert C to its numeric. Then we'll add it. So its numeric was 97. We add 3 to it, give us 100. That's why it printed out 100. But if we want to actually see the character version of that, we would put char in front of that number. Now I'm saying, give me the character version of the Unicode value 100, which is a D. So the second we did math with it, it decided, okay, since you're doing some math stuff, you must be wanting to deal with the numeric truth about chars. Therefore, we'll go ahead and we'll stop doing things automatically for you, and we'll let you do your math. So this guy is the integer 97. We're adding to it the integer 3, which gives us the integer 100. And that's what it'll print out if we don't do anything special. But now I'm saying, okay, I have an integer after this, but I want you to go ahead and treat him like a char again, because he actually is a representation of a char. I mean, nothing keeps me from doing this. Here, let's pick our favorite number, 32. So this is going to say, give me the Unicode value of 32. I'm hoping it's something reasonable because some Eclipse's terminal only knows how to show ASCII characters. So let's see if it's something that it actually knows how to show. It is not. Let's come up with here's this is 64 is the ampersand. it should know how to show that one. So I'll just say, give me the character version of 64. And there's our ampersand. This terminal doesn't know how to do all the Unicode characters. It's like because some of these guys are going to be like Chinese symbols and stuff like that.
Yeah, I was asking because we also use chars to store operators.
And our operators were characters, right? As we went through our string, when we say char at, we're getting an individual character. So we're going ahead and we're storing that individual character inside of a char type. Now, we certainly could have stored our operators inside of a string. It would just be a string of length 1. But the problem with doing that is comparing chars to each other, saying, is this char equal to plus, is a lot easier than comparing strings to each other. And kind of to show you that as an example, let's say I say string A is equal to the plus sign. Then I say string B is equal to the plus sign. And I go ahead and I print out system.out.println A equal B. Is A and B the same thing? I'm also going to say, is A equal to the string plus sign? I'll also say, is B equal to the string plus sign? Is A equal to B? Are they the same? Yep, so that should be true. Is A equal to the plus sign? Yep, so we're going to say that's true. Is B equal to the plus sign? Yep, we're going to say that's true. So this should give me 3 trues. And it will. But it didn't give us 3 trues for the reason why we think it gave us 3 trues. Let me show you what I mean by that. This actually segues right into what we were about to talk about. So I'm saying string A is equal to plus sign. Now, I think I've mentioned before that in Java, it's a string-based language. So Java makes strings very easy to work with, and to the point where even though strings are object types, Java lets us work with them as if they're primitive types. Kind of lets us deal with them like they're ints and chars and those guys. So they give us this nice little syntax for creating strings that is different than how we would create any other object. So I call this guy Syntactic Sugar. Right? This is a shortcut way of writing this right here. Okay? So on the surface, we would say that this guy right here and this guy right here are identical to each other. They mean the same thing. And for the most part, that is a true statement. This kind of goes back to the discussion we had when we were talking about a mistake that Java made. So when Java decided to get rid of structs, because they said really an object is a class that has no methods in it is the same thing as a struct. Remember when we had that discussion? And the difference was that structs by default are passed by value. Objects by default are passed by address. Okay? So now, having said that, just keep that in the back of your mind for a second. Let's go back and let's apply the identical logic that we just did a second ago. I'm telling you that this guy right here is syntactic sugar for this guy right here. It's a shortcut. They mean the same thing. Okay? That's a 97% truth. I'll fill you in on 3% after I finish tricking you. All right? So right off the bat here, I say, are A and B equal? A is the plus sign. B is the plus sign. Are they the same? Yeah, so this should be a true. Is A equal to the plus sign? That should be true. Is B equal to the plus sign? Still true. If we apply the same logic we applied to it a few minutes ago, nothing should have changed, right? This will be false. This will be true. this will be false. Let's see that first. False, true, false. Okay, so now we look at it and say, wait a minute. What the heck? A couple minutes ago I said we had all those things were true, but not for the reason why we thought they were. This double equal sign thing here is for comparing primitive types. This is the primitive equivalence operator. So it only works on the primitive type values. That is byte, short, int, long, char, float, double, Boolean, and then one invisible one called a pointer. Okay? Remember we talked about pointers as it relates to Java, where Java removed the special syntax for pointers, but they're still found all over the place. Objects are always passed by address. Okay? Strings are objects. So when we say, is this string equivalent to this string, we're saying, is this guy's memory address the same memory address as this guy? That's what we're saying there. When I built A, I set it equal to the string literal plus sign. And what happens here is that string literal, because Java wants to try to be as efficient as possible. So when I say the string literal plus sign, Java's going to say, okay, I'm going to go over to I got a little shoebox over here. I'm going to look at all my string literals I currently have for this particular program. Right? And Java's going to say, oh, do I already have a plus sign in here? I don't. So I'm going to go ahead and put one there. And that has a little memory address. So ultimately, this guy will hold the memory address of that plus sign literal. This next line, even though I've told you that first line is syntactic sugar for the second line, it's mostly a truth. And this actually has to do with what we were about to segue into anyways. This guy right here, that new keyword. I like to think of the new keyword like our real estate agent. Its job is to find us a memory address where we can build our value. All right? So when we ask the new keyword to do something, it's going to go out and talk to the operating system on our behalf and come back with the address. In real life, if I tell a real estate agent I'm looking for a two-bedroom, two-bath condo, and I say just pick whatever one you like, they're going to come back and say, okay, here's the address. This is where you live now. Right? So I'm going to drive to the address, whether I looked at the house, sight unseen, right? And that's my new address. That's what the new keyword does. But because I specifically said I want to create this string, the string plus sign, using the new keyword, as opposed to relying on any pre-existing string literal, what this guy is going to do is the new keyword is not going to look in the little string literal shoebox. It's going to say, this isn't one of those guys. He might look, the contents might be the same, but he's actually a different dude. Therefore, I'm going to go and find a nice plot of land out here in memory and bring you back that memory address, the memory address where I have built that plus sign. So we have a guy up in memory up here with a plus sign. We have a guy in memory over here with a plus sign. They both are plus signs, but they live at different memory addresses. All right? So when I compare A and B to each other here, I'm comparing the memory address of the thing in the shoebox to the memory address we just put up there. Those are different places. Even though the value that lives within them is the same, they are different locations. Okay? No different than if you live in one of those communities where all the houses look the same. But, the guy up the street who has the same house as you, he does have a different address, right? Your house is not his house. It just looks like his house, right? That's what's going on here. Now, when I say is A equal to the string literal plus sign, the answer is yes, because A holds the memory address of this guy in the shoebox, okay? The plus sign string literal. Then I'm saying, is he equal to the plus sign string literal? I'm not asking is it equal to the contents of it. I'm saying, go and find this memory location. Find where this dude is stored. So Java's going to go to work and it's going to say, oh, well, do I have a string literal with a plus sign in it? It's going to look through the shoebox like, oh, right here. And here's his memory address. And it happens to match the same memory address as A. Doesn't make sense for us to store the plus sign string literal twice, does it? That would be inefficient. I mean, when does it stop? How many plus signs are we going to store before things get out of control? We're only going to go beyond the string literals if the programmer specifically tells us, I want some new memory. Okay? So this is true because the memory address of A is the memory address of the string literal plus sign. This one's false because remember B points up to there. This guy is the string literal plus sign, which points down to there. Different places. That's why that's false. That makes sense? So when we use the equivalence operator here, we're not comparing the contents of the string. We're comparing the location of the string. Go ahead. Yep. Let's answer this first, and then I'll tell you how. You're probably about to ask, how do you compare the contents, right? Yeah, I'll tell you in a second. Go ahead.
What if we what if we declare a new string C equal to plus string plus.
Oh, string plus like that?
And remove the first A, variable A, string variable A.
So you want to get rid of that guy?
Yeah, so would the C be equal to B?
No.
Because you said
I understand what you're saying. Did the order make a difference here?
yeah.
Yeah. So no, because this guy was not a string literal. This guy is, as soon as I say the new keyword, I'm saying, this is something special. Don't use your automated systems. Do what I'm asking you to do. Build me a plus sign out there, and he's my special little plus sign. All right? Because I used the new keyword. I said I want to buy a plot of land.
Do we have a name for the memory address we use for new?
Or do we have to use new every time?
Well, new is the real estate agent. Your real estate agent doesn't just have a memory address. So when you hire a real estate agent, they can go and bring you back all sorts of addresses depending on the type of house you looked for, right? That same real estate agent, if you say, okay, I want a 2-bedroom, 2-bath condo, and then the next day you say, okay, I want a 4-bedroom ranch, they're going to give you 2 different addresses, the same real estate agent. So this guy doesn't have a memory address. It produces memory addresses. It brings us memory addresses. So now, are you asking, can I get the memory address of B?
No, I'm just trying to know if there is a name for the memory address that we use for new. New brings us a memory address, right? That's different from C's memory address.
Correct.
So,
But so let's say this. Let's say I said string A is equal to new string plus sign like that. I'm calling upon the same real estate agent twice and saying, find me memory for this guy, then find me new memory for this guy. Okay, so this is the same real estate agent. Let's call her Connie. Okay, so I call up Connie, and Connie is going to find me a plot of land for this guy. That's going to be one memory address, 123 Main Street. Okay, and then she's going to find me a plot of land for this guy, and that guy is 345 Elm. Okay, Elm Street. 2 different plots of land that I am building a very, very, very similar looking string at. Okay, so in this case, A and B would not be equal to each other. Okay, because the new keyword would give us 2 different memory addresses. Because once she gave us this one, that memory address would be blocked off. Nobody else is allowed to use that because it's currently been reserved for B to use.
Okay, so anytime you want to call upon it or whatever, you have to use string B. You have to use string B to actually get back the
Well, if I want to get, you only say string when you're defining it. So in this case, if I want to get the value that actually lives there, I would just say println B. And that would give me a plus sign. But so would println C or println A. Those guys would all give me things that looked identical to us. But they may live, all 3 of those guys live in different places. This lives in one memory location. This lives in another memory location. And this guy lives in another memory location which may be shared with other variables that choose to not use a new keyword but instead rely on Java's string literal memory manager. Okay, so Java says, oh, here's a string literal, no problem. I'll go ahead and store that for you here so that if anybody else wants to use that same string literal, we won't have to recreate it. We already have it here. Okay, this is no different than integer literals, except all the integer literals are already spoken for, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But what if I say this? What if I say int d is equal to 125? Well, 125 is an integer literal, but it's not something that's built into, it's not one of our single digits, right? 0 through 9 we knew about ahead of time. Outside of that, we couldn't predict what values our programmer might come up with, right? So what we just did with 125 here is the same thing we were doing with our strings. We went and looked around in the literal box over here. We didn't find a 125 integer type in there, so we went ahead and created a little location for him and then put him in there. That way, from that point forward in that program, if anybody else references 125, it'll talk to the same place in memory. So we're not storing 125 50 different times. Store it once. Makes sense, right? So with that in mind, if you want to know if A and B contain the same string, not that they live in the same place, but that they have the same content, strings have built into them a method called equals. And what equals does is it says, is this string, is the contents of A the same as the contents of B? So if we drop back to this, let's just get rid of some of the extra fluff. So A and B were both created with a new keyword, so we know they're at different memory locations, right? So we'll take out that guy. A dot equals B should be true, because even though they live at different places, they contain, case sensitive and all, the same string. Make sense? So this first line will be true. They are equal to each other as far as strings know how to compare their contents to other strings. This guy, though, will be false. This is comparing their memory addresses. A and B indeed live in different places. So this will be true, the first one. Second one will be false. Make sense? So with that in mind, it's a fair statement to say you should rarely, if ever, use the double equal sign for comparing strings. It's a common mistake a lot of beginning programmers make, especially when you consider I tricked you into it at the beginning when we got all the right answers for all the wrong reasons. That make sense? We were comparing memory addresses, but it just so happened that the answers came out the way we expected them to come out, and that could be tricky. So we have to know why things are coming out a certain way. But the reality is the only time we should ever be using the double equal sign as it relates to strings is if we specifically are talking about the memory address of that guy. So only if we are not discussing the contents of the string, only if we are saying, is this string the same as this string? Not do they contain the same crap, are they the same? Okay? Okay, so if you have a piece of paper with my home address on it, and I have a piece of paper with my home address on it, both of those pieces of paper point to the same house. Not a house that looks like it, the same house. Make sense? All right, so only use the primitive equivalence operator when you're comparing memory addresses. Otherwise, you should, for strings have a built-in equals method that allows you to compare strings. They also have another version of this called equals ignore case, which isn't going to help us too much here. But if I say LOL and I say LOL, those guys will now be the same. So equals ignore case will return true for A equal to B because it's ignoring that those guys, it's ignoring case sensitivity. So this will be true when I just had equals in here, it would be false. That makes sense? All right, so kind of segueing off of that, this new keyword is used in many different places. We're about to explore it as far as it comes to arrays. You will rarely see people use the new keyword with strings, but you will see people use the new keyword when creating any other object in Java. So that's where strings become a little bit problematic from a teaching perspective, because they're always the first object you teach because Java is so reliant on them. But at the same time, they are the only object that acts like a primitive. So they don't act like any of the other objects. So it's kind of hard to introduce objects with the first one being a string when the first thing I have to say is that strings don't act like the rest of the objects. Literally, strings are the only ones that act different. Every other object you would create using the new keyword, except strings. You can create it with a new keyword, and you might believe that you're doing the identical thing, but the reality is Java allows you to create string literals. Okay, but if you created a, say, like a car object, what does it mean for something to be a car literal? That's not like a known value type for us. Strings are a known value type, so Java lets us get away with it. All right, so let's go back in here. So this new keyword, from our perspective, gets us memory addresses. Whenever we see the new keyword hanging around, we should highly, highly, highly suspect we're dealing with a memory address. Okay, because that's what that new keyword does, is it finds memory addresses. So in here, when I create an array, so I'm naming my array AR, it's of type integer array, and I'm asking my real estate agent to go and find me a big enough plot of land to hold this many of these guys. Okay, so now ints are 32 bits or 4 bytes in size. So I need, 4 bytes. So I need 16 bytes of memory in order to hold a 4-bucket integer array. So we come down to our picture here. When I do this, what's actually happening here, and let's just go with, I'm going to assume these are at memory address starting at 100, just to keep the math easy. So that's 100, that's 103, 107, 111. Actually, let's do, this will work. So the value of AR here, when I create this array, what it's doing is it's going and finding me a plot of land big enough to hold 4 integers. So let's just say that the new keyword found for us memory address 100. That's the beginning of my array. It says, you know what, if you go to memory address 100, from there forward you have enough space that I've reserved for you to hold 4 integers. The value of AR is not the array. The value of AR is the memory address where I can find the array. Okay, and we can see that as an example here right off the bat. So I'll come in here. We'll create our int array AR is equal to a new int array of size 4. And then I'll do a system.out.println AR. And our gut feeling is going to be that, oh, well, that's going to show us the array. Well, I said, whenever we see the new keyword, we should be highly, highly, highly suspicious that we're working with memory addresses. And we always are, including with strings. Just so happens that strings do a pretty good job of covering their tracks. So we can't actually see the memory address of a string, even though we've just proven that they exist because we've seen it with the double equal sign trying to compare strings. But arrays are not so lucky. When I print out the value of AR, I'm not going to see an array. I'm going to see a memory address where an array lives. Crazy memory address. My version of that guy, though, was 100. So I didn't have to write such a scary number. So it just so happened that the real estate agent went and found me a nice convenient plot of land located just right up the street here at memory address 100. Okay? But it went ahead and it reserved all the memory up to 112 for me. Because each of these is capable of holding an integer. I wanted this guy to be able to hold 4 integers. All right? So my first integer will live at memory address 100, and it will take up 100, 101, 102, and 103. That's the chunk of memory that will be needed to hold those 4 bytes. Okay, those 4 little spots. So that means the next integer actually starts at memory location 104. 104, 105, 106, 107 is where integer 2 will live. 108, 109, 110, 111 is where integer 3 will live. 112, 113, 114, 115 is where integer 4 will live. So all of the memory from address 100 to address 115 has been blocked off for my use. So if you think about this in real life, I've told my real estate agent I want to build a 3,000 square foot house. All right, give her the rough dimensions or whatever. Well, they're going to go out and they're going to find me a plot of land that's large enough in size to fit that house on it, right? But, usually most houses, you have the house, but then you have kind of a yard too, right? Not in computers, okay? When I send that real estate agent out and I say, I want to build this house on it, they bring me back a memory address, which is the perfect size, no yard, all right? Wall to wall, you're squeezed in there perfectly, all right? So this guy can hold exactly this many of these guys. No more, no less. Now at this point, I'm not actually storing any integers. I've just reserved some memory so I could put some integers there. It's 4 integers in 12 different memory locations. Because each of those integers is taking up 4 bytes. An integer is a 32-bit value. So that means it's taking up 4 bytes to store one integer, 32 zeros and ones. So if you want to think about it, I can expand this out, and the first integer would take up the first 4 buckets. The next integer would take up the next 4 buckets. The next integer would take up the next 4 buckets, and so on and so forth. So what I've done is I've abstracted this and said, this bucket right here is all the memory between 100 and 103. So there are 4 buckets here, if you will, to hold my 4-byte version of my first integer. Because integers are 4-byte values or 32-bit values. That's how big they are. That's what kind of space they take up. If these were chars I was holding, chars are only 16-bit values or 2-byte values. So this would be 100, 102, 104, 106. Because they take up less memory to hold. To hold 4 chars takes up less physical space than to hold 4 ints. That make sense? All right, so, but what's kind of important about arrays here is that arrays require contiguous memory, which is a fancy way of saying memory right next to each other, which we've already seen. We've already talked about this, right? When I asked my real estate agent to go and find me enough memory to hold 4 integers, it's already bringing me a plot of land all next to each other. Okay, when you want to build a house, that is a 3,000 square foot house, it wouldn't be acceptable for the real estate agent to come to you and say, you could build half your house here. Then the next quarter you can build up the street. And finally, the last quarter you build downtown. That doesn't work that way, right? Okay, so the way we build houses is like how we build arrays. Like, I want it all in one place. Okay, and there's actually a good reason for that. We'll talk about it in a minute, but we want it all right next to each other so we can plan ahead, put it all right next to each other with the ultimate goal of being fast. All right? Arrays are very fast. They're also memory inefficient. All right, so if we think about this in a real life example, if you have somebody who builds, I mean, it's pretty common for people to have too much house, right? Way more house than they need. You got, 2 people living in a house with 12 bedrooms. Okay. I mean, if they have a lot of family that comes visits very often, maybe. But generally speaking, that's a waste of space. And from a space next to each other perspective, if you go out and ask the real estate agent to give you a plot of land big enough to hold your 12-bedroom, 18,000 square foot house, that's going to be a pretty big plot of land, right? Okay, and you're only going to be utilizing a very small portion of that plot of land at any moment in time. Maybe you're occupying, 1/12 of the house, or maybe 1/6 of the house if you're really spreading out. Okay, but generally speaking, you're not using the house very efficiently. So most of that house is wasted space. But does that mean that somebody can move into, can build a house in your, second floor? No, that space is reserved for you. Okay, so you've wasted a lot of space because nobody else can use it. That make sense? So arrays are like that. When we ask for a 4-bucket array like this, I'm saying I need enough memory to hold 4 integers. Okay, so I need 16 bytes of memory next to each other to build my house. Whether I actually end up putting integers there or not is insignificant. It's mine. That's my memory. Nobody else can use it. Make sense? So with that in mind, it's memory inefficient. But because all that memory is right next to each other, it's fast. I'll show you why here in a second. So what has been created right here from this line of code is something that in memory looks like this, but the variable AR holds the memory address of the beginning of this guy. So we would say that AR points to the beginning of the array, where it starts. Okay? And we have knowledge that from that point to however long the array is, in this case it's 4 buckets long, all that memory has been reserved for us. All right?
So thinking about this in a real life application, would the programmer be telling the computer how many buckets to reserve?
Oh yeah. So if you said, hey, I want to store 10 numbers, you would say I need an integer array capable of holding 10 numbers. The alternative, if you said, I want to hold, well, no more than 100 numbers, but I might only need to hold 3. If you're going to do this with an array, well, you can be, I guess we could say lazy, but it's not necessarily a bad idea, and just say, just go ahead and create me a 100-bucket array. I'll use of it what I want, but at least I have it. Okay? Because the issue with arrays, the kind of a bad side effect of them, is especially since I advertise that they create the perfect size for them. So let's say you just spent all this money building your 12-room mansion. All right? And then you decide, you know what? I want to add a sunroom. Well, in real life, since we usually have a yard and a little bit of wiggle room, you can squeeze a sunroom in, right? Not with arrays. With arrays, you're saying, oh, okay, you want that sunroom? No problem. We'll just rebuild your mansion over here with a little bit extra space for your sunroom. You move in over here, we'll destroy this house. That's memory inefficient, right? Computers, who cares, right?
We can't create dynamic sized arrays.
Arrays are fixed size, just like a house would be. If you think about this in real life, if the plot of land for your house was exactly the size of your house, just hug the walls, okay? Adding a sunroom, if you were just, I'm adding this sunroom, would require you to get a new house, right?
So
There's no room to squeeze a sunroom on.
if I want a chunk of memory, but I don't know what size, what alternatives do I have instead of arrays?
For right now, nothing. But the next class, we'll learn about linked lists and vectors and things like that. So there are other options that are,
Since we don't have
but they're slower. That's the trade-off. So, if I give you the foreshadow when we say the competition, who's the array's competition? I'd say the array's competition is something called a linked list, or things like linked lists. Well, linked lists are malleable. They can shrink and grow in size to our heart's content. But the way they pull that off is by being relatively slow.
Well, we don't have structures in Java, so what do
We don't have what in Java?
Structures.
Well, correct.
What do we use for the classes?
Yeah, we would create classes for a linked list. Yeah, and we do that. That's what we end up doing in the 537 class. We look at the alternative. But now the important thing here is not to think that arrays are the beginner version of this and linked lists are the better version. Depends on what we're doing. Okay, arrays are fast, and a lot of times fast is good. We got tons of memory in our computer. Who cares if we're wasting it? In a computer, you want to build your sunroom. We don't have a room. Destroy this. Build a new one over there. Got the sunroom. Done. Who cares? This machine has 16 gigabytes of RAM in it. And I'm a little upset that Apple wouldn't let me add more. This is their brand new machine. But for today's uses, 16 gigabytes is plenty of memory for pretty much everything. How many integers can I store in 16 gigabytes of memory? I just built an array of size 4. An array is 4 bytes. An integer is 4 bytes. Okay? I have 16 gigabytes, so if I multiply that by 1024, that's megabytes. I multiply that by 1024, that's kilobytes. I multiply that by 1024, that's bytes. That's the number of bytes of memory that I have. I divide that by 4, that's how many integers I can store in my system memory. 4,294,967,296. It's a lot of numbers. Right? So this is only a problem if we're storing a lot of numbers. If you figure that your average array is size, 10 or 20 or 100, something like that, it's nothing. It's a drop in the bucket. You want a new one? Hold one more thing? Build a new one. Memory will just waste that memory. That we have in Java, we have this thing called automatic garbage collection. So it'll come around and it'll just say, you're done using this memory. Let me wipe that up for you. We'll let the real estate agent resell that for you, no problem. And move on with life. So even though in real life it makes no sense for us to burn a house down to add a sunroom, computers would do it all the time. No big deal. Well, no. Arrays store collections of like type values, which means I could just as easily have changed this guy to say I want to store a char array for chars. The difference that would have actually happened there, though, is this would be 102, 104, 106, only because the size of a char is 2 bytes instead of 4. It just happens to they take up less space. Right? But all this same stuff is happening under the hood. So here, we'll even work with this guy as a char array. So if I want to put stuff in this array, because right now all I have is a variable called a variable called AR, which points to the beginning of my array, tells me where to start. I know that my array is indexed bucket 0, 1, 2, and 3, just like strings are. So when I have a string that has 5 characters in it, the legal buckets are 0 to 4. When I have an array with 4 things in it, legal buckets are 0 to 3. Okay? Same as strings, you don't have to memorize 2 different things. But now if I want to actually put stuff into the array, I would say something like this. AR at bucket 0 is equal to W. AR at bucket 1 is equal to O. AR at bucket 2 is equal to O. AR at bucket 3 is equal to T. Now I filled in my array with some values. If I want to print out what was at bucket 0, I access it the exact same way. So I can say system.out.println AR at bucket 0. And that will print out the W. So one important difference between char arrays and strings, which are effectively collections of chars, right, is that char arrays are read and write. I can set an individual bucket. I can also grab the value at an individual bucket. With strings, I can get the value at an individual bucket using char at, but I cannot set the value at an individual bucket. If I want to change the contents of a string, I have to build a new string using concatenation. That make sense? Now, let's talk about that speed aspect of this. When I say AR at bucket 3 gets the value T, this guy right here is actually turning into something. Let me show you this. AR at bucket 3 is equal to AR plus 3 times size of, in this case, since it's a char array, size of char, which is the same thing as saying, well, AR is base address 100 in this case, plus 3 times size of char. A char is 2 bytes in size, right? 3 times 2 is 6. So this is 106. So this says, give me whatever's at memory address 106. That's bucket 3. So it's fast because we don't have to start at the beginning of our array to get to that last bucket. I can compute the location in memory where bucket 3 lives because all those buckets are right next to each other. That's why this contiguous memory thing is important for arrays. It makes them fast because it makes all the positions in them, I usually call them buckets, the buckets in the array, it makes them computable. We can find exactly where they are using quick math. And we don't have to do the math. All we say is set AR at bucket 3 equal to T. And under the hood, what's happening is Java is going to the base address of the array, then going at an offset of 3 times the size of the thing, size of whatever you're working with here. In this case, it's a char. From that, we land on 106. Give me the value there. Make sense? So this is how arrays work under the hood. So it's all about memory and traversing memory. As programmers, we don't have to deal with it, but we should know it exists. In older languages like C and C++, where we had a specific syntax for working with pointers, or working with memory, we could actually set an array up manually, do it our own way, and then we could access individual buckets directly from the memory location. So in C, I could say something like this. Instead of saying AR at bucket 3, I can say AR plus 3 times size of char, give me the value that lives there. That's what that says. So everything that's in parentheses here ultimately comes down to a memory address. Base address 100 plus 3 times size of char, which is 2. So that's 106. So everything I have highlighted there turns out to be the memory address 106. You put an asterisk after that, which says, give me the value at that memory address. It'll give you that guy. Or you could just write AR at bucket 3. Those two things mean the same thing. Now, most people would say, I like this better. And most of the time you'd be right. But every now and then, it might be handy to be able to directly manipulate memory. Every now and then. Can't do it in Java. Okay, so it's a drawback that sometimes, on a very, very rare occasion, a programmer might be solving a problem that is an uncommon problem that might benefit from it. So you could go through an entire career as a Java programmer, never missing pointers, never missing the memory, so the ability to directly manipulate memory. May never cause you any problems. Okay. So that is the theory stuff behind arrays. Now let's look at arrays in practice here. So I went ahead and I built an integer array with 4 buckets in it. Right now I have nothing inside that array. I can go ahead and put some values in there if I want. What I'll do, just since it'll be helpful for your homework assignment, I'm going to go ahead and introduce you to generating random numbers. So it's another object, again, similar to strings, but the random object acts like every other object acts, where strings act more like primitive types. So I'll say random r is equal to new random. And this is going to want me to import java.util. So the random class lives in a different library. No big deal, it's built into Java. It's just kind of a secondary library of Java. The stuff that's available to us by default is the stuff that lives in java.lang. So that way when you write a program, you only are committing to that library as being part of your executable. If you want to start bringing in other third-party stuff, then now you're bringing additional code into your project, which then makes it bigger. But so in this case, I'm specifically saying, go ahead and give me access to java.util.random. And that class right here allows me to generate random numbers. So I'm going to go ahead, I'm going to fill up my array with some random integers. So I'll say for int I is equal to 0, I is less than ar.length I++. Now, one thing to notice here is when we dealt with strings, it was length with an open and closed parenthesis on it. For arrays, it's length without the parentheses. That'll make more sense, the difference, later when we start talking about writing our own objects. The difference is that this is a field versus for strings, it's a method. For us right now, so we don't have to go too deep into that, it's identical. Just arrays don't put the parentheses. The meaning is identical. All right? If a string has 5 elements in it, its length method would return the number 5. If an array has 5 elements, it was built to hold 5 elements. Regardless of how many elements are actually in it, it was built to hold 5 elements. Its length field would boil down to the number 5. Okay? Ultimately, it boils down to the same value in terms of its semantics. So what I'm going to do is, as I loop through every bucket of my array, I'm going to go ahead and put a random number there. So I'll say AR at bucket I is equal to r.nextInt. And what r.nextInt will do is it will give me a random number in the range of all integers. And integers are 4-byte or 32-bit signed numbers, so it's plus or minus 2 to the 31st power. So this will be some number between negative 2 billion and positive 2 billion. So each time through this loop, I'm going to generate a random number between negative 2 billion and positive 2 billion, and I'm going to stick it inside of the current bucket of my array. All right, then we'll come down here and we'll print out our array. And what do you think the output will look like? I'm tricking you, by the way.
Just the memory address.
Memory address still, right? Okay. Sure, I've gone ahead and I filled up my array here. Absolutely, I absolutely have. It's no different than what we did back here. If I printed out AR before I put these characters in here, it would be 100. After I put those characters in there, it's still 100. That's where that guy points. Now, there is stuff there now. So if I want to start accessing the individual buckets, yeah, it might be helpful. So maybe what I do is I write a method, static void print int array. And this guy takes an int array as a parameter. And I say for int I is equal to 0, I is less than ar.length, I++. System.out.println ar at bucket I. So I've given myself a little tool that I can pass any integer array to, and he knows how to print that integer array. So what I'll do here is I'll say driver.print int array. I'll pass it AR. So this should give me now the contents of the array, not the memory address of it. Okay, because this function right here, this method, spins through every element of AR, whatever I pass it. Understand, I purposely picked AR based on your question from earlier. This AR is inside of your house. This AR is inside of my house. They have the same name, but they don't conflict with each other. All right? So when this guy dies, this version of AR goes away. Okay, so the fact that these dudes have the same name is just happenstance in this case. You know, I can call this guy Bob if I want to.
What we're doing is passing the resulting variable.
We're passing the memory address. So I create my array up here. I fill it up here. Then I'm calling my print int array, and I'm passing it the value of AR, which is going to be whatever memory address this guy points to. That's going to come into this variable here that I happen to name Bob. At this point right now, AR points here, Bob also points there. So I have two variables that happen to have different names right now, but a second ago they had the same name. But they both are pointing to the exact same memory location. Okay? Which means that this guy is being passed by address. Which means that if I change something in Bob, I'm changing that stuff here. Which means later on, if I start using AR to look at stuff, I'm going to notice those changes. If I hand you the address to my house and you run over there and spray paint the garage, when I get home, I'm going to notice a spray painted garage. Okay? So even though Bob and AR are two separate variables, and in this case they happen to have different names, before when I had AR and AR, they're two separate variables, they're both pointing to the exact same memory location. So any modifications we do up here will be permanent, okay, because we're changing it in memory. Now, it just so happens, though, that in here, I'm not changing anything. I'm just going through that memory location, printing out each bucket I find. Okay? So that's all print array does. So we'll see 4 random integers in the range of -2 billion to +2 billion. Make sense? Okay. So there's an array with some stuff in it. Now, something that, let me, just want to make sure I cover enough stuff. All right, so questions about arrays real quick. All right, let me show you one more thing quickly, and then let's take a short break because I need to make sure I get enough stuff, but some of you might want to run to the restroom or something. So we'll take like a 5-minute break in like 3 minutes. So let me show you about recursion here in a second. And you're not going to like it. It's going to be a little bit uncomfortable. So then you can kind of stew on that for the 5 minutes. Then we'll come back and review it. Okay? So we have this concept called recursion. Recursion is when a method calls itself from within itself. Okay, another way you can put it is when something is implemented in terms of itself. Now, the usual example for recursion is factorial. So, for instance, if we have 4 factorial, 4 factorial is 4 times 3 times 2 times 1, right? 4 times 3 is 12. 12 times 2 is 24. So this is 24, right? That's what that guy equals. But now the reality is that 4 factorial is actually equal to 4 times 3 factorial. 3 factorial is equal to 3 times 2 factorial. 2 factorial is equal to 2 times 1 factorial. 1 factorial is equal to 1. So this is an example where factorial can be implemented in terms of itself, as long as we have a stop case. So eventually we stop calling ourselves down here when we finally say, okay, 1 factorial, we've had enough. Okay, the answer is 1. And then every other call before that is finally able to resolve. So to write that, so that's the recursive definition of factorial. So factorial takes an integer n. If n is 1, we're done. Return 1. Otherwise, return the current value of n times the factorial of n minus 1. But this line right here cannot finish until this guy finally returns. So this current version of the method, it kind of gets put on hold. Okay, he's paused while the rest of the method keeps going. So 4 factorial will return 4 times whatever 3 factorial is. 3 factorial will return 3 times whatever 2 factorial is. Now, the 4 factorial has not returned yet, and the 3 factorial has not returned yet. Those guys are still waiting. Go ahead.
Yeah, I was going to say, if you want to keep that going, you have to loop it.
It is looping naturally. This recursive call here is effectively calling this guy a second time. So rather than looping in place where it's all within the same call, we're actually calling it once, and then we're calling this guy again. So if you look at it from 2,000 feet up, it's a loop. Okay? But it's a loop that's taken a lot of extra memory because each time we have to pause this version of the method, we have to put everything on hold. We have to say, well, for this current version of factorial, his version of n is 4. But for the next version, his version of n is 3. The next version, his version of n is 2. So on and so forth before it finally finishes. All right, so I'm going to come down here. We'll just say driver.factorial. I'll pass it the 4. This guy's returning an int, so I need to print that. All right, so this should give us our 24. There's our 24. If I pass it a 5, this gives us our 120, which is 5 factorial, so on and so forth. So it seems like it is running pretty quickly, right? We pass it 5,000, 500,000 rather. So this is going to give me a stack overflow exception. Yeah. So the way that recursion is implemented in programming languages is with something called a stack, which we also talk about in 537. It's another data structure. But that stack is not infinite. So basically, we only have enough room on the stack to hold so many recursive calls before we run out of memory for it. All right. So recursion typically gives us nice, short, elegant solutions because a lot of times if you were to see this written recursively, you would actually see them write it like this without the curly braces. So that whole solution is 2 little lines long. Right, so you get nice compact solutions with recursion. You also get, in many cases, very elegant solutions. I mean, it makes sense. 4 factorial is, in fact, 4 times 3 factorial. So why shouldn't I use my power tool here that knows how to calculate factorial? Just so happens it's a little bit expensive in terms of memory. But like our discussion a little bit ago, who cares most of the time, right? Unless you run out of memory. And just so you know, I didn't run out of memory on my computer. Java has a built-in maximum stack size. You can actually, through command line arguments, increase that to make it a lot larger. But you would have a finite number. You would be able to calculate larger factorials iteratively using a normal loop than you could through recursion, because recursion is having to store extra crap each time you make that recursive call. That makes sense?
Real life application?
Huh?
Real life
Well, I mean, that's a good real life application. So think about how many other things are implemented in terms of themselves. So, something like Factorial, I mean, realistically speaking, we might not be taking the Factorial some gigantic number. Another great real life application is going to be your homework assignment, which is called merge sort, which we'll be talking about here after we take a short break. Merge sort actually calls itself twice. So it makes 2 recursive calls. Okay? Now I promise you the solution to merge sort is actually quite short. But man, you're going to spend a lot of hours coming up with that much code. Okay? But again, it's going to be fun. And I promise you it's a lot harder than what you did for this week. But you'll probably end up spending a similar amount of time. Because now you're better than you were last week, right? I mean, we're all basically geniuses now. All right, so let's take a quick break, like 5 minutes, otherwise I won't be able to give you enough help on your homework assignment. I assume we all want the help on the homework assignment? All right, so let's do 5 minutes, come back at 9:24, and that should give us enough time for me to introduce merge sort.